All right. Hi, everyone, and welcome to this session. My name is Erik, and I'm one of the GC guys in the Oracle Java Platform Group. Today, I'm going to talk about something I call Paving the GC On-Ramp, and it's all about what we're doing to improve the usability of GC. In particular, my focus on ZGC. ZGC is a concurrent low-latency garbage collector, and what I mean by concurrent is that rather than stopping the application threads to perform GC, the GC continues running while the application is running. The reason why it's concurrent boils down to the goals of our project, which have been there since the inception. We have 3 goals. The first one is low latency. So we want to have really low latency with sub-millisecond GC pauses. The second goal is scalability. We want the ability to scale the heap from small heaps to large terabyte-sized heaps, and it should still work well. The last goal, which is more of my focus this talk, is auto-tuning and ease of use, which we take very seriously. So I've been working now on ZGC for a pretty long time, and the project has been running for a long time, so it makes sense to provide a bit of a status update where we are at. And in terms of the first goal, low latency, things are looking pretty promising. We have those sub-millisecond GC pause times, and pretty much all of the heavy lifting is done concurrently, and this involves a whole bunch of interesting GC stuff, such as marking through the live objects, scanning routes in stacks and global routes, and reference processing, unloading classes, moving things around, and reclaiming garbage. There's a lot of things going on, and it's all running concurrently. So that's pretty cool. In terms of the second goal, scalability, things are, again, looking very well. The latency doesn't really scale with the size of the heap, and neither does it even scale with the number of routes. So if you have lots of threads, the GC pauses do not increase. And one thing we've been working on lately is the generational version of ZGC, and it brings the ability to separate young and old objects, and this allows the GC to reclaim garbage among the young objects without having to scale with the size of the old generation. So you can have a lot of old objects, and the GC will be very efficient and just ignore it. So in terms of these performance-looking things are looking great. The layout of memory in ZGC is what we call a discontiguous region-based layout. So here's a bit of a visualization. It's a bunch of regions, they scattered throughout memory, and there's some holes in between where we don't have any mapped memory. And in terms of the concurrency aspect, while the application is running, we can collect garbage in the old generation, and while that old generation is being collected, we can have multiple young generation collections also running concurrently. So the GCs are concurrent to each other and concurrent to the application. So it's a very concurrent system. So what I'm going to talk a little bit more about now is the usability aspect, and it boils down to my belief that having an advanced GC shouldn't be your problem, it should be our problem. Paving the on-ramp is really something introduced by Amber on the language side, and there's been a lot of work on simplifying the initial user model exposed to new Java developers. And I think this is great. You see here that we made it a lot easier to run Hello World applications, and in general you can write simple applications, and it's very easy to do that. So what I've been thinking about is when these applications start evolving a little bit and you start messing around with heap sizes, maybe tuning a few things, and what I want to avoid is ending up with something looking like this when you want to run the application. So it's more on the running side that I've been focusing a little bit more. We don't want to see this. Sometimes it might even be that you need to configure the Linux kernel to get the last drop of performance out, and it would be really good if we could avoid doing these things as well and make it as easy as possible. Fortunately, with this third goal I was talking about, making things as easy as possible to use, we've had this sort of thinking from the beginning, and some of this craft you just won't see. So rather than, for example, having features that are expected to be turned on in certain situations where they're beneficial, we try to automatically identify what those situations are and heuristically turn them on. But we also designed a lot of the algorithms around ease of use. Because of that, there's some silly JVM flags that we just never really had in ZGC. And in the case of NUMA, this is one of these things, if you run on a large machine, it's very beneficial to have a NUMA policy. So of course, we rather detect that you're running on one of these systems and enable it heuristically. Then there's some really low-level things with unfortunate interactions between J and I object accesses that can cause starvation in the GC, and we avoid these things and change the algorithm instead to not have starvation in the first place. You don't need this stuff with ZGC. Another primary thing is that you have this trade-off, and trade-offs tend to lead to JVM flags because the JVM doesn't really know what the user wants. In particular, when it comes to latency, it's really hard for the JVM to know what latency the user expects, and since we don't know, we sometimes need JVM flags. And especially when you have a stop the world collector and you have to squeeze a really complicated operation into a small amount of time in a stop the world operation, it can lead to some interesting decision points that are hard to answer without JVM flags. With ZGC and a concurrent collection, we've sort of squished this triangle. So there are still latency aspects, but they're far fewer and they're less relevant. And it's still the case that, well, we don't know what latency the user expects, but having really good latency, it's probably good enough. And that makes a lot of these decisions easier. And it typically boils down more to memory versus CPU trade-offs. Because of this, there are many JVM flags that you don't need to worry about with ZGC that are concerned with trade-offs inside of the GC save points. Another aspect with the third goal, I mentioned auto-tuning. Sometimes there's a bunch of parameters where if you can find really good numbers, you can improve the GC performance and the performance of your system. Especially with a generational collector, it's even more the case that there's some really tricky things that are hard to figure out. One such thing is how large should the young generation be, and how long should objects stay around in the young generation before they get promoted to the old generation. But also, when should an old generation collection start? What should the trigger be? But then you think about also how many threads should we be using when we're collecting the generations, and what if they're both running at the same time? What should the balance be of threads between the two GCs? These are hard questions, and it's easy to turn to JVM flags, but we have not done that. So with generational ZGC, we've designed the algorithm such that there is not even a concept of a capacity for the generations. The boundaries between the young and old generations are very fluid. And in fact, how we decide to balance the memory between the two generations is based on cost modeling, and it figures out what the balance should be automatically. And a lot of this comes down to improving the memory CPU trade-off. So because of this, you don't really have to specify how many GC threads to use, let alone how many for each generation. And in fact, it even adapts while you're running. So it might be that you start off with a rather low allocation rate. We start doing GC with a set of threads. And if there's a burst in the workload, we dynamically adapt to the new situation and start using more threads. So it sort of figures this out automatically. And many of these generation-related JVM flags, you don't need any of them either, and most of them don't even aren't even recognized by ZGC because the concept doesn't exist. And I think this is pretty cool. So now that we removed a bunch of JVM flags, this is currently where we are at today, that there isn't a lot to configure, but we sort of expect at least a heap size. So some form of heap size configuration, and then you might also want to throw in some large pages if you want good performance, and make a decision about when memory should be paged in. And this is where I want to go to the next level. If you don't set the heap size, you get a default. And this default currently is 25% of the machine memory that's available on the machine, but it's capped at roughly 32 gigabytes. And that is the max heap size across all of our GCs, if you don't set it. And so that's rarely what you want. So typically people set a heap size, and then you wonder, well, how do I set a heap size? How do I derive this number? A common way of doing it is you run some heap size, get out of memory, you continue increasing the heap size until eventually you don't have out of memory exception anymore. But then are you done? Well, a trained eye might start looking at GC logs and find that there is an allocation stall, that even though the application is running, it might be that, for example, the latency is pretty bad because the concurrent GC isn't able to keep up with the application allocation rate. So this is something we want to avoid. So then you might increase the memory again, but then when you start looking at it, it runs and runs pretty well, but it could be running better because there's still quite a bit of CPU utilization due to GC, and would be even better if you had a larger heap. But if you use too much memory, then you get into a situation where you run out of memory on the machine, and then the application will die. You don't want to have that either. So eventually, you find the right balance where the application seems to run well, at least as long as it runs predictably. But even then, it might be that there are fluctuations in the workload where you have a phase where it's running on a low allocation rate, and then you get a huge burst. And then you occasionally get an allocation stall anyway, even though you had a lot of memory headroom. And there are manual heap sizing ways of dealing with this. One of them is softmax heap size. This brings us to yet another JVM flag, that you can specify a lower softmax heap size that's lower than the max heap size. And what this does is to tell the JVM, try to use as much memory as softmax heap size, and make that your goal, but never exceed the max heap size. This gives a little bit of a memory buffer in the discrepancy between these two heap sizes for unpredictable situations. But then it's quite difficult to measure the extent of unpredictability, because unpredictability in its nature is unpredictable. So I would like to get into a better spot with automatic heap sizing that I've been working on for a while now. And the goal is to shrink this configuration service further so you don't have to configure the heap size. So let's go back to this squished trade-off triangle that I showed before. You might notice that with the latency being a far smaller thing in this triangle, mostly CPU and memory being left to trade off between, that there's a difference here that CPU and memory, they're resources. Latency isn't a resource, but CPU and memory are. And this is pretty nice because resources, the reason you're trading CPU versus memory typically have something to do with the availability of these resources. And this is something that we can monitor and figure things out automatically. We can also monitor and find out automatically where we get to a point of diminishing returns in terms of increasing the heap size. But we can also reason about which resource is more or less scarce. So the idea is to do a whole bunch of monitoring. It's monitoring CPU, both on a system level and on a process level. But also, within the process, we're looking at how much of the CPU is being spent of GC compared to other things. And similarly for memory, we're doing a bunch of monitoring there as well. We're monitoring the amount of memory use available in the system, how much is used by the process, and within the process, how much of the memory is being used by the GC. And using this, we can do a bunch of reasoning and figure out the heap size automatically by modeling these resources as forces that push the heap in opposite directions. So hopefully it can then get into a balanced resource usage automatically. The first of these forces, I call it the weak GC force. And this is all about trying to increase the heap to reduce the CPU utilization of the GC. But it's also equally as much about avoiding allocation stalls. With automatic heap sizing, we always prefer taking memory that's available on the machine compared to stalling, as long as you're not critically low on memory resources. So if there's more memory available, just allocate it instead of stalling. And in the beginning, we start with a very small heap size of 16 megabytes, which means that we have to grow very quickly in the early phases, which this algorithm does. And then eventually, we'll start converging at a point of diminishing returns, where we're happy about the heap size. But there's also a dynamic nature to this, that the point of diminishing returns sort of changes based on the circumstances. For example, if the CPU utilization is very high, there's more of a point to try and push it down. And similarly, if you have a lot of memory or very little memory, it might make sense to make different decisions about what kind of GC CPU utilization you want. So it's quite clever about trying to reduce the likelihood that the user is actually going to have a problem. The other force I call the strong GC force. And this one is concerned with trying to keep the memory used within the boundaries of the machine. We don't want to use more memory than we have available on the machine. And there are really two policies here. One that is more long-term and slower. If we see that the heap is bloated, we try to push it down a little bit at a time so that eventually it will converge at a lower point. But if there's urgency involved and memory starts to become a little bit critical, then it will increasingly aggressively just uncommit memory as fast as possible to avoid running out of memory on the machine. I think it's good to reflect a little bit on what the impact is of such an algorithm. One of the most obvious impacts is how it converges at a nice, good heap size without the user having to specify anything. That's pretty good. It relieves you of having to specify the heap size. But at the same time, there's also something to say about this buffer of memory that we need for unpredictable situations. With manual heap sizing, this buffer is stored inside of the heap. So the discrepancy between the max heap size and the soft max heap size is this memory buffer. Whereas with automatic heap sizing, this memory buffer is outside of the heap instead, because all the memory that's available on the machine is at our disposal to avoid allocation stalls. So finding how large that buffer needs to be becomes unnecessary. Another impact of this that's worth mentioning is the relationship to native memory. It might be, for example, that you have an application, you found a good heap size, but after a while something starts using more native memory. And what I mean by this is, for example, it could be that the application is using more direct map byte buffers. Or alternatively, it could be that we're just in time compiling more methods and the code cache needs more memory, or loading more classes and the metaspace needs more memory. This can be really hard to reason about as a user, but with automatic heap sizing, what will happen when the native memory grows is that this will start to apply pressure, because the less availability of the memory, it acts a little bit like a spring that starts pushing the heap size to shrink a little bit. And that way it balances out automatically and shrinks the heap to accommodate the extra native memory. On a related note, this also affects how the JVM interacts with other processes. If you have a JVM running, you have some target heap size, and we converge at a point that's nice, but then someone starts running another JVM, for example. What will happen is that the memory availability drops, and again, this works a little bit as a spring, and it starts pushing both of these two heaps. However, since the originally running JVM is more bloated, that means that that's the one that's going to shrink the most. In fact, the other one will keep growing, and eventually it converges at a point where both JVMs are happy, and it still have some buffer of memory available for unpredictable situations. I think this is pretty cool. In fact, I think it's worth looking at this example that shows how this works in practice. Here we have 3 applications running, and on the y-axis, we have plotted the heap capacity being used, and while on the x-axis, we have time in seconds. There are 3 applications, SpecJBB 2015 running at some fairly high injection rate, and then there's an H2 database application that uses a bunch of memory, and there's a Cassandra application as well. It has mostly, in this case, native memory, so the heap capacity stays pretty low. We see that when SpecJBB 2015 starts, I said that it would have to grow the heap very rapidly in the beginning, and as you can see, it delivers on that. It starts off growing very, very fast in the beginning. And when the H2 program starts, it also similarly tries to grow its heap very rapidly in the beginning. But there's a liveness spike in the H2 database program where it needs a lot of memory. And SpecJBB 2015, on the other hand, it just wants to use more memory, but the heap isn't very dense. And what happens is that the memory availability drops, and the system adapts so that SpecJBB 2015 starts shrinking its heap to make memory available for the database application so it can progress past its liveness spike. After a while, we start running the Cassandra application, which puts some extra pressure on the system. And when this liveness spike drops in the H2 program, we see that there's a surge of memory in SpecJBB 2015. Now that there's more memory available in the machine, it immediately starts grabbing more memory to improve its performance. And similarly, when the H2 program terminates, you see similarly that there's a surge in heap capacity for SpecJBB 2015 to increase its performance, and at the end it increases even further, and we get to its convergence point where the benchmark wants to be running at a larger heap size while still having some memory available to deal with the unpredictable situations where you get an allocation stalls. So yeah, I think that this showcases pretty nicely how can deal with unpredictable situations that would be very difficult to deal with static heap sizing. With this, I believe that we can finally remove the need for configuring heap sizes. And it looks like we're only left with 2 JVM flags here. What if we could do something about that as well? Let's talk about large pages. But before that, we need to understand what is a page. A page is an OS primitive that tells the hardware how to map virtual memory to physical memory. And it comes in two flavors, small pages and large pages. The main difference is that the small pages have a often 4 kilobyte granularity, whereas the large ones have a 2 megabyte granularity. That's 3 orders of magnitude different granularity. So you're wondering, what's the big deal? The big deal is that these entries need to be cached by the hardware. And a usual result of using large pages is that the performance of the application improves by roughly 15%. And this is a pretty big deal. In fact, it's not uncommon for this to be more important than the choice of GC algorithm. And then you might wonder, why don't you just have large pages on all the time? The reason why is that there's a trade-off and it's difficult. And this trade-off goes back to the OS itself. It's hard for the operating system to know when and where to put large pages. If you put it in the wrong place, then you get memory overheads. And if you do it at the wrong time, you get latency problems. There's a system called transparent huge pages in Linux that tries to do this transparently. Unfortunately, though, it isn't very transparent, and it tends to get both the when and the where wrong, which is unfortunate. The JVM can help a little bit. If you supply the use transparent huge pages JVM option, then the JVM will tell the OS with a hint, please use large pages here and here. And that's good, but it only works if the configuration of the Linux kernel is correct. And unfortunately, by default, it tends not to be. And this problem is even worse for ZGC because it's using shared memory instead of anonymous memory. And if you want to know more about how to configure this, I think you should watch Stefan Johansson's presentation from FOSDEM. It was also about what we're doing to improve the usability of ZGC. The other approach to large pages is explicit large pages. And the idea is to try and find a good answer for when and where these pages should be allocated. The when is before the JVM even starts. So you create a pool in the kernel, you create a pool of large pages. And when the JVM starts running, it can take memory from this pool. The trouble is, though, that for this to work, the user has to specify how many large pages the user needs. And this question is even harder to answer than what the heap size should be, because you need to account not just the heap itself, but also a bunch of native memory. And it's very difficult to configure. So it isn't very user-friendly, let's put it that way. And of course, the idea of these explicit large pages is fundamentally opposite to the idea of automatic heap sizing. So that's a bad fit, in my opinion. The last problem I'll talk about for these JVM options is a trade-off between startup and warm-up. And I call this heap priming. The concern here is that when you initialize the heap, there's some work that you can do up front, or you can leave it until later. If you do it up front, then warm-up will look good. Whereas if you do it later instead, you have the opposite effect. One of these is the initial heap size, which can be configured with XMS. If you set it to the same value as the max heap size, XMX, that will commit the entire heap up front. And when we do that, that takes a bunch of time. It can take a pretty long time to do, but all the memory is available up front. Similarly, always pre-touch is a JVM option for ensuring that the initial heap size is paged in right off the bat when you start running your application. And this also has a startup overhead. So you get into a situation where you have to choose whether you want good startup numbers or good warm-up numbers, and you have to select one of those. And that's why the JVM options is because it's not obvious to the JVM which one the user wants. But I'm all about having the cake and eating it too. So to deal with this, I worked a bit on something that I call concurrent priming, where we try to have both good startup and good warm-up. The idea can be visualized like the following figure, that we have a concurrent thread that concurrently commits memory while the JVM is running, sort of like curling. And it's also heating up the memory so that it's quick to access. And when I say heating memory, well, this is where, for example, this paging I was talking about fits in. Since this is done concurrently, we can ensure that the memory is paged in and committed before the application starts using it, but also without spending any startup time in the initial phases of the VM execution. And the very interesting thing is that this sort of solves the large page problem as well, because now we can tell the kernel when and where to apply large pages. Why? Well, we know that we want large pages in the heap, and this concurrent thread is pointing out where that heap is. And the when can also be answered because the latency overhead that's associated with upgrading pages to be large might require some defragmentation, for example. The latency impact of that is absorbed by this concurrent thread that doesn't affect the latency of the application. Therefore, we found this sort of sweet spot, I think, where we can just get the 15% performance boost without suffering any of the negative consequences. And even better, you don't need to specify any interesting Linux configuration files, because this system pierces through the configuration and just tells the OS what to do, regardless of the configuration. So I think this is pretty cool. And with concurrent priming, we can then finally remove the last two JVM options here. And we can also remove all this need for configuring the Linux kernel. So this is starting to look pretty easy to use now. Unfortunately, there is one more thing. There is one more Linux configuration that you might need. But fortunately, it's limited to when you're using very large machines. So now we're talking about hundreds of gigabyte machines. Then the OS restricts the number of mappings you're allowed to use. And this is sort of annoying, but it needs explicit configuration. We have been working on this as well, and some of this work started with JDK 21. And to understand that better, let's talk about pointers. The references, the object references, are embedded as something called colored pointers in ZGC. And before generational ZGC, we had these 3 metadata bits in the high order bits of the pointers that were implemented by mapping the same virtual memory 3 times to the same physical memory. And this allowed us to deal with the various concurrency perils of writing a concurrent GC. But the cost was 3 virtual mappings to the same physical memory, and that requires more memory mappings. With generational ZGC, we increase the number of color bits that we need to 12. So we sort of knew that this is too many bits to use multi-map memory. We can't do that. So instead, we did something that I call colorless roots, where the in-memory representation of the references uses a whole lot of colors, but they're low-order bits. And when we load these pointers to a register, the colors are stripped off, and we end up with something that looks a lot like a normal address. And this way, we can reduce the number of mappings we need by 3 times. So this helped quite a lot in reducing the need for configuring this flag. But we're doing more as well. We've also been spending a lot of time lately on how we represent the memory that's free in ZGC. What we have today is something that we call a region cache. What happens is that essentially when memory is freed, and in this picture it's the orange regions, when they get freed, they place in a cache. And when allocations happen, the cached regions are reused. And one unfortunate aspect of this is that it leads to some virtual address space fragmentation. While that doesn't really cost any physical memory, it does increase the number of mappings that we need. So we spent some time on figuring out what to do about this and come up with a new concept that we call the mapped cache. And instead of caching the regions, we're instead caching ranges of virtual address space that's mapped. And with this scheme, we can represent the free memory in a different way that allows us to allocate memory in a more fragmentation-tolerant way. The result of that more fragmentation-tolerant allocation scheme, and additionally some defragmentation from the GC, is that the number of holes in the virtual address space is reduced a lot, which means that we're using less mappings. So this is great. This allows us to use a whole lot less mapping, and you're less likely to run into this configuration problem. But we're not stopping there. We're also collaborating with the Linux team to try and get this solved once and for all, and get to a point where the entire heap can use a single mapping, and the holes in the memory can be encoded straight in the page table in the kernel. And that will really alleviate this problem entirely. And then finally, we can get rid of the need for the users to ever deal with this Linux configuration file. And in summary, that means that we can go from, this configuration mess on the left to using only a single JVM option, use ZGC. And if you use that, you don't have to configure all of this stuff. And I think that's the ultimate goal. And not much more to do there. So yes, thanks for listening. So if there are any questions, please go ahead and grab a microphone.
Erik, some of this work could apply to other GCs, like large pages. Was it also done?
No, and the reason why is that you need to have this concurrent priming, really, in order to find a place where you can explicitly tell the kernel, this is the time to upgrade this page to use large pages. And I mean, I'm not going to rule out that we're going to do something similar to that in the other collectors, but this is something that we're going to start doing in ZGC. All right, well, as a final note, I'd like to say, main point of my talk is that when you upgrade the JDK, not only do we get the performance benefits that we've been talking about a lot, but we're also improving the ease of use to make it easier for you guys to use the JVM without having to go through all of these hurdles. So thank you for listening.